We start with the nth order differential equation. We wipe out all the terms that are not first order. And essentially we can just combine the a1 of x and g of x and simplify to a single g of x. And this right here is the simplest form of a differential equation. It's the first order and it doesn't have any constants or coefficients. We can go ahead and multiply the dx over, integrate it, and we get the constants for each integration out. Now these constants can subtract over and combine into a single constant. And the integral of g of x dx typically is just the antiderivative, and we usually rewrite it as a capital G of x. And this right here is the solution. Now let's go back to our differential equation. Now say we multiply another equation in terms of y next to it. Now we can see that there's two equations. We have equation in terms of x and equation in terms of y. And since they're a product, they're essentially separate from each other. So you can imagine they're separated from like an invisible line. So this is what makes them a separable. This is what makes a separable differential equation. Now, a good way to see this is through an example. Say we have the following. If we rewrite it such that all the x's are on one side and all the y's are on another, we get this. We can clearly see the g of x, which is x e to the 3x, and h of y, which is y squared e to the 4y. So this categorizes as a separable differential equation. Now the goal of this differential equation is to, in order to solve it, is to put all the y on one side and all the x on the other. So we proceed. Divide the h of y over. Now the 1 over h of y can be treated as another function py. But there's one caveat here, and it's that since h of y is in the denominator, you want to keep an eye on domain issues where h of y would equal 0. So substituting the py in, and then integrating, we get the constants of integration, and just as before, the integral py and the integral g of x can be seen as antiderivatives, so we rewrite them with the capital form. We combine the constants and we get our solution. Now this differs from the previous case, the non-separable, such that we had the y by itself before, but now we have a function of y. And essentially that changes the whole ballgame, because now p of y can't always necessarily be solved in terms of just y itself. In other words, this form right here is an implicit solution. And in order to get into an explicit solution, it's not always doable. And you will see more of that in a bit. Now for some examples. Example 1. Y prime plus 2x times y squared minus 1 equals 0. Rewriting y prime and dy dx. We subtract 2x y squared minus 1 over, so we have dy dx by itself. And now we can see how it's kind of separable. We see the function of x, 2x, and we see the function of y squared minus 1. And like I said, imagine the invisible line separating them. Again, the goal here is to have the y's on one side and x on one side, separating them. So, divide the y squared minus 1 and multiply the dx. Now, can we integrate this? Not quite yet. How can we further simplify y squared minus 1 or 1 over y squared minus 1? Well, if we break this, the y squared minus 1, into the following, y plus 1 times y minus 1, recall that it represents a partial fraction decomposition. Ideally, what we mean by that is we want to separate the two fractions and solve for a and b such that they end up equaling this, which is essentially just 1. So in order to do that, what we need to do is multiply y minus 1 next to a, then multiply y plus 1 next to b. And we have the following. Now, if we let y equals 1, we could see that the a term will cancel out because 1 minus 1 is 0. So we're left with 2b equals 1, and b equals 1/2. Similarly, if we let y equals 0, we will now get b minus a equals 1. Substituting in for b, we can solve for a, which is negative 1/2. Now plugging a and b in, we have the following. We can multiply the 2 over. And now can we integrate? Yes, because now we're at a position that we can integrate. So we integrate. And we get the natural log of the absolute value y minus 1 minus the natural log of the absolute value y plus 1. And then on the right side, we have negative 2x squared. Now we can apply our natural log difference rule, where the natural log A minus the natural log of B, essentially the natural log of their division. So we can get natural log of y minus 1 over y plus 1 equals negative 2x squared plus c. We can get rid of the natural log by applying e to the power of each side. And then we get this. Y minus 1 over y plus 1 equals plus or minus c e to the negative 2x squared. We have the plus or minus because we're undoing an absolute value. But since we have a constant c, the plus or minus doesn't really have any meaning, so we can just replace it with. Now here we can technically stop because we can say that this is an implicit solution, but can we make it explicit? Definitely. First, let's clean all this up so we have a clean slate. We start with multiplying the y plus 1 over. Now, for the further steps, since there's going to be a lot of moving terms around, in order so it doesn't get messy, I'm going to substitute a coefficient to represent the term c e to the negative 2x squared. So, c to the x. Distributing the c to the x, subtracting cxy 1 over, and then adding 1 over, factoring out the y, then finally dividing the 1 minus cx. We have our explicit solution. But we're not done yet. Let's substitute for cx back in. And now we have our solution, our explicit solution. So how can we visualize this? Let's go ahead and generate the slope field, and let's see how the curve fits in it. So this right here is the slope field, and already we can see a curve for c equals 3. Now notice how if you move it from between 0 to 10, how our curves change, but they stick to the slope field. Now if you go in c equals negative, we can see the opposite, how the curve is taking on a different profile. Now going back to the range where c is between 0 and 10, you might have noticed these areas right here where the curve doesn't exist. What these are essentially asymptotes. Now you can see them more clearly. They're essentially locations where the denominator was equal to 0. In other words, where 1 minus c e to the negative 2x squared equals 0. Now if we solve for this, we can actually find the equation for the lines. So let's do that. We divide the c over. We take the natural log on each side. Then obviously doing the property of quotients, but reversing it. Natural log of 1 is 0. So we're left with negative natural log of c equals negative 2x squared. Cancel the negatives, and then apply e on each side. And then take the square root. We get x equals plus or minus the radical of natural log of c. And these are what the two asymptotes are, the positive of this and the negative of this. Now on to our second example, which will break down in two parts. So for our first part, we'll have x in the numerator and the y in the denominator. So dy dx equals negative k x over y. Now we could have a fixed constant, but I want to keep it a variable k for analytical purposes, as you'll see in a minute. So let's get the x and the y's on one side. Next, let's integrate. And upon integrating, we should get y squared over 2 equals negative k x squared over 2 plus c. Now let's get the c on one side and everything else on the other side. And we have the following. We can multiply the 2 over and just incorporate it into RC. Now we can further break it down into explicit solutions, but for the purpose of explanation, I'm going to keep it as implicit because there's something you might know here. This equation is actually an equation of an ellipse. More precisely, the equation of an ellipse looks like this. Y squared over a of y squared plus x squared over a of x squared equals c. And this becomes apparent when we realize that k here is essentially a of y squared over a of x squared. Okay? And how is this an ellipse? Let's take a look at it. So we have our two elliptical cases. We have the first case where our ellipse is more vertical. And we have our second case where the ellipse is more horizontal. Now, the reason why we have a of y and a of x is because a of y is essentially the axes in the y direction, and a of x is the axes in the x direction. Okay? Now, this is important because as you'll see in a minute, visually, if a of y is greater than a of x, or in other words, if k is greater than 1, we have the vertical side dominating, so our ellipse is more vertical. But if a of x is greater than a of y, or k is less than 1, then we have the horizontal side dominating. Now how can we visualize this? Let's start with the case where the magnitude of k is greater than 1. Clearly we can see that it's a vertical ellipse. Now, what if the magnitude of k is less than 1? It is more of a horizontal ellipse. Now what if it equals 1? Then it's a circle. Now, if you increase c, essentially what you're doing is you're basically shrinking it or making it bigger. Now, if c equals 0, it vanishes to a single point, and then c equals negative, it doesn't even exist. Okay? Now there's one scenario that we didn't mention, and we didn't really go over it, and that is when k is negative. Now this is where something interesting happens. So let's say c is back to being positive. So what happens when k is negative? So our ellipse is stretching, 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 and at k equals 0, it is two horizontal lines. But now if we get negative, what we get instead is, this is what we call a hyperbola. Okay? Now k is negative, but the magnitude of k is less than 1. So just as for ellipse, when the magnitude of k was less than 1, it was more horizontal. Here, the hyperbola is more horizontal. It's more stretched in the horizontal direction. So if the magnitude of k were to equal 1 and k were to equal negative 1, we'd see that it would neither be a horizontal or a vertical. It'd be pretty equal. So imagine these lines as y equals x, and these lines as y equals negative x. And now the moment we have the magnitude greater than 1, it's back to being more vertical, as you can see. Okay? Now, right now c is positive, but what happens if c is negative? The only thing that happens is, so as we're getting closer to 0, we're getting closer and closer and closer to touch the horizontal axis. Okay? Now that it's 0, we pretty much touch it. Okay? And now that we're negative, now we're breaking into our pieces, but flipped. So before we had top and bottom, now we have left and right. Okay? And similar logic applies, where magnitude of k is greater than 1 is more vertical. When magnitude is 1, it's pretty equal. Again, you can see, and then less than 1 magnitude is more horizontal. You can see it stretching. So we would have to summarize this into a table. Okay? So starting from the top, where we have k is greater than 1, and that's essentially the magnitude of k is greater than 1, or the magnitude of a of y is greater than the magnitude of a of x. We start with the entry where k is a negative. Okay? Now, in this case, what we saw was a hyperbola, but more in the vertical direction. So if you go through our c's, when c was negative, it was a vertical hyperbola, both top and right. When c equals 0, it was equal. So they were touching at the crossing. With c equals positive, it was left and right. Okay? But now with the magnitude of k less than 1, we see that the hyperbola is more horizontal. And similar pattern follows. With negative c, it's top and bottom. With 0, they're touching. Positive c, we have left and right. And last but not least, we have a hyperbola, but they're equal. They're not going towards the vertical, and they're not going towards the horizontal. So, and we can see this in action one more time. Negative c, top and bottom, but you can see the diagonals are virtually y equals x or y equals negative x. They're touching for c equals 0, and for c equals c greater than 0, they're left and right. Okay? Now, for k being positive, we saw that they weren't hyperbolas, but they were in the elliptical class. So for the magnitude of k greater than 1, we see it's a vertical ellipse when it's c greater than 0. And for magnitude of k less than 1, it was a horizontal ellipse. Again, only for the case where c is greater than 0. Okay? And last but not least, we had a circle when k was 1. So c greater than 0, we have a circle. Now, for all these cases, for the elliptical cases where k is less than 0, whenever c was less than or equal to 0, they vanished. So this simple differential equation, dy dx equals negative k, x over y, defines a whole set of conic sections. And that's what these are, they're conic sections. Isn't that quite beautiful? One simple equation can describe so much math and so much. Now, on to our second part of our second example. Now, before we had x in the numerator and y in the denominator, but now we are flipping it. So, first things first, let's get all the x's and y on their own sides. Next, let's integrate. And upon integrating, we get natural log of y or absolute value of y, equals negative k, natural log absolute value of x plus c. We take e to the power of for both sides. The e and the natural log cancel for the left side. And then we got the plus or minus, which is from undoing the absolute value. Now the plus or minus and e to the c can just be combined into one constant. And by using the natural log property, we can move k or negative k to be a power of absolute value of x. And now we can undo e and the natural log, and we're left with y equals c over absolute value of x over k. And this is our solution. Now how do we visualize this? Now we can see that for the negative c, essentially we have these two 1 over x-like solutions on either side. Okay? So this is for the negative c's, and this is for the positive c's. Now, the asymptote is at x equals 0 because that is the only place where the denominator equals 0 at x equals 0. Now, what happens if we move k around a bit, making k more larger? We can see how the corner of the curve is getting sharper and sharper. And this is ideally representing how the powers are getting more exponential. Because typically when you get more exponential, your curves, your rise or your decline gets sharper. So that's one way to think about it.